blessing on their students as we go through math elements of all this and for their understanding. Pray for our tennis team, Lord, that you'd give them success in their matches and that you'd use that in their lives to help them get where they need to get for wherever they're going after this. I pray this in Jesus' name. Amen. All right. We are... Oh boy. We're going to talk about condensation of vapors and vapor pressure so that we can eventually get some math. Okay. So condensation is pretty easy, right? And we've got vaporization. And we need to talk about dynamic equilibrium. And vapor pressure. Okay, so condensation. Change from the gas phase to the liquid phase is called condensation, right? We probably tend to associate this with loss in temperature, also increase in pressure. Those two will certainly do that, right? To a certain extent, this happens naturally. If you had a jar with a lid on it with water, right? Some of that water is going to be present in liquid form, and some of it is going to be present in vapor form. And there's going to be a constant change where some molecules are escaping, and the increase of escaping is going to cause others, as they get near, to be captured, and so there's going to be a certain amount of condensation, and that will not necessarily, you won't necessarily experience these, but it's a natural process. One escapes, one loses, etc., etc. Vaporization obviously is the opposite of this. So as we increase our temp, or as we decrease our pressure, right? This idea of dynamic equilibrium is what we were just explaining, that if I have a jar, closed, at all times I'm going to have, or nearly all times, I'm going to have water escaping as vaporization, and I'm going to have water condensing as a liquid, right? If I had an open jar, given enough time, this will all evaporate, right? If I had a closed jar and I opened it, let me go back to that. There's a pressure that builds up in here, a partial pressure of the water vapor. And so as this builds up, it's going to reach a point, water's going to escape until I build up enough of a partial pressure there that I reach it. If I were to release this lid and let it all out and then put the lid back down, well, I've already lost some water to vaporization. Now it's going to do that again. Okay. Think of a soda bottle. So you got carbon dioxide dissolved in the soda, and you pop that thing, and immediately, right, the bubbles start coming out. It's doing its thing. And the soda bottle is pretty full and pretty new, and you put the cap thing. This is definitely how it worked when I was a kid. And it's not going to have much CO2 left in it, right? And that's due to this, right? It's all about these processes that we're talking about. Let's see what this has to say, okay? When the rate of condensation becomes equal to the rate of vaporization, neither the amount of the liquid nor the amount of the vapor in the container changes. The vapor in the container is then said to be in equilibrium with the liquid. Keep in mind that this is not a static situation. Molecules are continually exchanged between the condensed and gaseous phases, such as an example of dynamic equilibrium. The status of a system in which reciprocal processes, for example, vaporization and condensation occur, dynamic equilibrium is the status of a system in which reciprocal processes occur at equal rates. So they're happening, but there's no net change. This is an easier way. Pressure exerted by the vapor in equilibrium with a liquid in a closed container at a given temperature is called the liquid's vapor pressure. Okay, so let's consider that. The pressure exerted by the vapor is called the liquid's vapor pressure. So the pressure that the vapor is exerting back down. And this is temperature dependent. So if I, let all the vapor out and I close it back down, it's going to evaporate or it's going to vaporize until that vapor pressure returns to whatever it is. And you'd have to find that out experimentally to find out what it is. And again, it's going to be different for each temperature. Okay. The area of the surface of the liquid in contact with the vapor and the size of the vessel have no effect on the vapor pressure. Right? So if I have a little water, if I have a lot of water, if I have a little test tube, or whether I've got a big, those things do not affect what the actual water vapor is. Now, the surface area that it's exposed to does affect the rate that this happens at. It may happen faster or it may happen slower until it reaches dynamic equilibrium. But at dynamic equilibrium, it will have the exact same vapor pressure, assuming the same temperature. All right. Well, let's roll on. We've got a few more concepts to cover. Chemical identities of the molecules in a liquid determine the types and strengths of intermolecular forces or intermolecular attractions possible. Consequently, different substances with different equilibrium vapor pressures. What did we just say? The chemical identities of the molecules in a liquid determine. Okay, so what is it? What are intermolecular forces? These are the things that are going to determine our vapor pressures. If I have some lightweight non-polar molecule, that thing's going to dissolve very, very easily, right? If I have some very dense, superpolar filled with hydrogen bond molecule that's big and heavy, it's not going to evaporate very easily, right? And that's essentially the concept. So it wants us to do something with that. So we get this. We're given a bunch of stuff. You don't have a book, so I'm just going to draw this up on the board. We are given CH2, and we're given I'm going to run out of room. I'm going to write smaller. And we're given HH. Okay, so these are species that we're looking at, and essentially we want to think about which one of these is going to have the highest vapor pressure at a given temperature, right? Which one of these is most readily going to vaporize, which of these is going to least readily vaporize, right? So as we do this, you're looking for those intermolecular forces. Does it have dipole moments? Does it have hydrogen bonds, right? So let's just quickly identify what you see. What do you see happening here?
That's the hydrogen bond.
Okay, so hydrogen bonds here. Any other hydrogen bonds?
Both two there.
Okay.
This one, two.
Okay.
In the middle.
How about dipole?
There's between the carbons there.
Right here. Okay. Is just London's for our highest vapor pressure. We'll call these A, B, C, and D.
C is the highest.
C is the highest, okay. And then
I think A,
A. Okay, followed by
B, and D.
B and D.
Yeah.
Okay. It's probably going to be
D and B.
B, D, and then B, I believe, but let's double check that. See what they have to say. Ether, that's this one, is a very small. Why does it just give it to us in the right order? Ethylene glycol has 2 hydroxyl groups, therefore, like water, it exhibits extensive high bonding. It is much larger than water and thus experiences larger London forces. Its overall IMFs are the largest of these 4 substances. So we've got it. Okay. Okay. All right. Wants us to do another one. We'll go ahead and do that. Next one, it says at 20 degrees centigrade, the vapor pressures of several alcohols are given in the table that I'm going to give you. Explain these vapor pressures in terms of types and extents of IMF. So we've got CH3OH, we have H5OH, we have C3H7OH, and we have C4H9OH. Before I even give you anything, which one of these do you expect to have the highest vaporization pressure and why?
I think the smallest one.
Smallest one, why?
They're both.
They all have one hydroxyl group, so one region where they're likely to have hydrogen bonding. Okay.
But the London forces are smaller on the smaller one.
Okay. Less London forces, less mass, less to overcome. So yeah, your thinking is absolutely right. Right. So this would be number 2, number 3, and then number 4. And so we see that. This is 11.9 kilopascals. This is 5.95 kilopascals. This is 2.67 kilopascals. And this is 0.56 kilopascals. Okay. So even though this is larger and heavier, right? It's more likely to vaporize. Excuse me, did I do that exactly backwards? Am I telling you exactly backwards? Yeah, I'm doing it. Yeah.
This is less.
Yes. Less likely to vaporize because of the weight.
Yeah.
Okay. All right. As temperature increases, the vapor pressure of a liquid also increases due to the increased average kinetic energy of its molecules. I don't even want to mess with that one. Let's go to boiling points for a second. Erase this. All right. Where'd that marker go? There it is. Boiling points. When the vapor pressure increases enough to equal the external atmospheric pressure the liquid reaches. So, BP occurs when vapor pressure equals atmospheric pressure. So this explains why water will boil at a much lower temperature when you're up at altitude, right? Because there's less atmospheric pressure, so we need less vapor pressure before they're equal, and then it will boil off, right? Or the same thing, if I have water in a vacuum and I suck the air out of it, right? There's minimal or atmospheric pressure. Well, that requires minimal vapor pressure, and it'll just begin boiling. Or if I put it under great pressure, right? You got a pot on the stove and you got a lid on it, and it's super hot, but it's not boiling, and then you lift the lid, and all of a sudden, boom, right? Because I've actually reduced the vapor pressure by letting it, or the atmospheric pressure by letting it out. And so now it's going to run. Okay. The boiling point of a liquid is the temperature at which its vapor pressure is equal to the pressure exerted on the liquid by the gaseous surroundings. Okay, so that's another way of saying it. It is temperature at which the equilibrium vapor pressure is equal to the pressure exerted on the liquid by the gaseous. Yeah, it's the same thing. They just said it fancier. For liquids in open containers, this pressure is due to the Earth's atmosphere. The normal boiling point of a liquid is defined as its boiling point when the surroundings pressure is equal to 1 atmosphere. So, normal is when Vp equals 1 atmosphere. 101.3 kilopascals. It's going to be an important number for us coming up. Okay. They give you a pretty graph. I'll draw the graph. Why not? This is going to be my 101.3 kilopascals. This is going to be my temperature. The more or the stronger intermolecular forces, right, the higher the temperature we're going to have before we can achieve that. So you think about something like water, right? The water is going to boil at something like what temperature? 100 degrees Celsius, right? Of course, if I lower the pressure, I can lower my temperature. Something like ethyl ether, which has relatively few, it's going to achieve it at a much lower temperature. In between, we can do like ethyl alcohol. That's, the alcohol that's in all the drinks. Then you get something like ethylene glycol. Well, good luck getting it to boil. Yeah. So this has everything to do with the character of intermolecular forces, and that's why this is useful to think about. All right. Let's go to this. We're skipping sample problem 10.6. It's reading a graph. You can do that. That's not worried about any on that. You're doing great. Let's do this Clausius. That's a fun one. It's got to be Greek. Clausius Clapeyron. That's not Greek. Does it sound French to you?
Yeah.
Probably coming out of the Renaissance.
That's French.
That's French, right? That's got to be Greek in origin. Maybe Roman. Okay, so here's the Clausius-Clapeyron equation. We don't even care about the name, you just care about the parts, and you got to be able to use them. Oh my. You're not even going to have to use this first form of it. Okay. So this is, technically speaking, the form, and I'm sure that they derived this experimentally and did all the things and got this. But this is really hard to work with. And so they have simplified it. I guess we should talk about it. So this is the enthalpy of vaporization of the liquid. Okay. You know, that's the ideal gas constant, but which ideal gas constant are we going to use? We're going to use the one that's 8.1, no, what is it, 8.3145?
8.314.
8.31, they want you doing 8.3145. We're going to carry it out that far. Okay, T is going to be my temperature, right? And what is my A? A is a constant whose value depends on the chemical identity of the substance. Okay, great. But if I don't know this, like, you know, what's this going to do for me? So, the linear equation, maybe, all right, what do they have to say about this? Temperature must be in Kelvin in the equation, and that's going to be true for us. If you don't change it to Kelvin, you're going to get a crazy answer. Trust me, I was doing it during the break. This equation is often rearranged into a logarithmic form to yield this linear equation. So this is the one that we want. So we want ln p equals negative delta 8, and this is still no. Look, we're not doing any of that. You can almost forget all this, because this is, they're just proving to you how we get to the one that we're actually going to use. And it's much like logarithms. I don't understand natural logs, but I know how to hit the button in the calculator, and that's really all we need to do. So here's the equation that we're going to use, okay? We're going to use the natural log of pressure 2 over pressure 1 equals delta H of vaporization over R times 1 over T1 minus 1 over T2. And this will work every time, okay?
I think the log is to, because if you use log is to get the exponential fraction control down.
Yeah.
It's the only thing I know.
So they give you the proof for this in the book if you want it. I'm not wasting my time with it. Let's get some math. Okay. I'm going to erase this other side. I'm going to leave that equation up because we want it desperately. Okay. So isooctane has an octane rating of 100. We don't care about that. It is used as one of the standard. We don't care about that. Here's what we do care about. At 34 degrees C, the vapor pressure is 10.0 kilopascals. Okay. At 98.8 degrees C, its vapor pressure is 100 kilopascals. We want to find the delta H of vaporization. Okay. So essentially we're going to solve for this. So it would be really useful, first of all, to rearrange our equation, right, to solve for this. Okay, so what's my first step going to be? Here. or we want to get to where we're solving for that, and then we'll plug in our numbers.
To pass that to the other side.
I would not plug numbers in first. That's going to be a disaster. Okay, so what do you want me to do?
You need to divide both sides
By,
by the delta H.
that's not going to work out yet. Remember, I'm solving for this.
Oh. So maybe divide first by the log, the natural.
Let's think of it. Let me rewrite this.
Okay.
This is A equals B over C times D. I want to solve for B.
Okay. So you can divide by D
So I'm going to go A
over D.
over D, right, equals B over C, right?
Now you multiply by C.
Yep, so now I'm going to get A, C over D equals B.
But I was just doing the hard way around.
Yeah, you're on the long way. Let's keep it super, I can do A, B, C. All right, with that as our basis here, we're going to go the natural log of
B2
P2 over P1, right?
divided by
Divided by 1 over T1 minus 1 over T2, right? And now I need to multiply this by R, right? So
times R.
I'm going to put the R over here. R times the natural log of P2 over P1 divided by 1 over T1 minus 1 over T2 is going to equal my delta H of vaporization. Okay? So we need to be able to manipulate, we're going to do another manipulation of this problem coming up, right? In fact, we're going to be solving for this later on, which is a whole other thing. But for right now, this, and we should be able to plug everything into this, right? So we're going to get 8.3145, and then I guess units matter, right? So let me go ahead and do that. 8.3145, and it's going to be joules per mole, degree Kelvin. All right, I'm going to multiply that by the natural log of 100 kilopascals over 1,000, or I'm sorry, over 10 kilopascals. Right? And now I'm going to divide all of that by 1 over, now this is where I got to remember to put this into Kelvin. If you forget to do that, this ain't going to work, right? So,
73.15.
273.15 plus 34 equals 307.15.
Yeah.
And this is minus 1 over, now I want 98.8 plus 273.15. So I get 371.95. Something wrong there. No, that was right. Okay. All right. Okay. So let's start with this. 1 divided by 307.15 minus 1 divided by 370.95 equals 0.0033567.205. Okay. I'm going to take the natural log of 100, I'm going to take the natural log of 10, right? And it did. 33,800 joules per mole. Joules per mole or is it kilojoules per mole? Kilojoules per mole.
Got the same.
Good. Okay. Well, let's take a run at the next problem then. At 20 degrees centigrade, the vapor pressure of ethanol is 5.95 kilopascals. At 63.5 degrees centigrade, the vapor pressure is 53.3 kilopascals. And we're going to try to solve for delta H, right? So we run into that same manipulation situation where we've got to solve, well, I guess we already did it and we left it up there, right? So R times natural log of P2 over P1 divided by 1 over T1 minus 1 over T2. Okay? So we can begin with our R, right? So 8.3145 kilojoules per mole degree Kelvin.
Yeah.
You believe? Okay, and now I need to multiply that times the natural log of my P2 over my P1. So 93.15 degrees Kelvin minus 1 over, and I'm going to let you do the next one.
It's 279.
What are you making this up?
It's 273 plus 6.35, isn't it?
Yeah, I just don't trust myself to do it in my head.
279.5. No, not 5. 15 plus 35.
I need the wrong numbers. Okay, 273.15 plus 63.5 versus 6.315.
I think it's 6.35.
It should be 63.15. So you can't trust me. Okay, I fixed it. All right. So this is our equation, right? I never trust myself, so I'm going to break it down by parts. Not trusting me is gone. So 0.000440779 degrees Kelvin. Okay. Now let's do our natural log. So I need natural log of 53.3 divided by 5.95. Get 2.1925112. Okay. So So I do 8.3145 times that divided by that. Aha. There we go. So 41,360. Yeah. Kilojoules. Is it kilojoules per mole? Per mole. Okay. All right. Let's take a step back and just make sure we understand why we're looking at this, right? So I can experimentally determine this. At a given temperature, what is my vapor pressure? That can be measured, right? And the same thing at another given temperature. So what's the relationship between this, right? What is my delta H of vaporization? Which, if I know that, will let me determine the vapor pressure at different temperatures, or the temperature to get a different vapor pressure, right? So once I know that, I can determine any other component of this, right? So it is a useful thing. We've spent all our time determining it. Now this time we're going to have it, and we're going to determine other things from it. All right. So, new problem. For benzene, the normal boiling point is 80.1 degrees centigrade. And the delta H of vaporization is 30.8 kilojoules per mole. Now what it's asking you to do is find boiling point at 83.4 kilopascals. So this is, they're actually saying this is Denver, so you're at altitude, so we're less than our standard, right? This is less than an atmosphere because we're high up. Okay. So we know we're given this, right? I have a T1, I'm solving for T2, I'm given a P2, what's my P1?
It will be the atmosphere.
Yeah, so what,
So
103.3? Right, okay. So it is 103.3, isn't it? Remember, we're solving for T2 over here, right? So we gotta work backwards, right? So let's begin with natural log of P2 over P1. Now, how am I going to mess with this algebraically?
You can divide by delta H over R.
Break those down into two pieces. What's the first thing I'm going to do?
Divide by delta H?
Nah.
Multiply by
multiplied by r, right? So
Yeah.
r, let me make that simple. R times natural log P2 over P1 equals delta H times that, right? Now I can get rid of my delta H. I can go, hey, delta H, vaporization, and that's going to equal 1 over T1 minus 1 over T2, right? Okay. In fact, I don't even need those parentheses anymore, right? So now my next step is,
Gonna subtract 1 over T1.
yeah. So I'm going to go R natural log P2 over P1 over delta H vaporization. Where am I at? Minus
1 T1.
minus 1 over T1 equals negative 1 over T2. I'd like to get rid of that, so I'm going to multiply everything by negative 1. It's going to do that, right? Okay. So now what's my next step? Because I need this on top, right? There's two ways we can think about this. We can either just go, okay, we need the reciprocal, so multiply everything by 10 to the negative 1. Or I could go a long way, and this is how I tend to do it. I go, okay, I'm going to multiply by T2. That equals 1, and I'm going to divide 1 by all of this, and that will give me this. It comes out the same, right? So I can either go negative r times natural log of P2 over P1 over delta H vaporization plus 1 over T1, and I can do all of this to the negative 1. I can say that equals T2, and it does. Or I can also say that 1 divided by all of this is the exact same thing. Okay. Your choice?
I think 1 over, it's easier to see it. It's
The
gonna-
far right one?
Yeah,
I agree.
it's gonna give the answer like straight away.
It's also easier on the calculator
Yeah.
to me. Oh, you get it. So let's go ahead. Let's work with that one. They come out the exact same. And the parts, you know, once you have this or that, you're golden. Okay.
Yeah.
So 1 over. What are we looking here for here? We're going R, which is going to be 8 point, what is it? 3145 kilojoules per mole degree Kelvin. All right. Times the natural log of, well, my natural log is my pressure 2 over my pressure 1, right? So 30.8 kilojoules per mole, divided by,
It's 83.
that's not right, what am I doing?
83.4.
Wrong
Overall.
thing. Thank you. It's because yeah,
You got the one.
yeah, I'm not to be trusted. Kilopascals over 101.3 kilopascals. Okay. All right, we're good there, right?
Mm-hmm.
Oh, I forgot something here, didn't I? Yeah, okay. All right. All this over delta H of vaporization, right, which is 30.8 kilojoules per mole, right? Now my one other thing that I need here
Plus 1.
is to go plus 1 over my temperature, which is 273.15 plus 80.1. Ooh, didn't make it.
1 over 80.1.
Okay. So we can start to put this into some parts. I'll change markers so I don't confuse everything. You already saw it?
Yeah, I guess.
What'd you get?
I got 0.02, but I think it's wrong.
I don't think that's right.
Yeah, it's because
Yeah.
I'm seeing out the temperature.
Let's make sure we're doing everything right here. That's right. That's right. That's right. That's right. Everything we've done so far is great. It's just going to come down to making sure we put it correctly in our calculator. Like I say, I like to break it down a little bit before I go into it. So I'm going to go 8.3145 times, and I'm going to go ahead and figure out my natural log here. 83.4 divided by 101.3. So that's negative 0.194438102. I'm going to run that back just to make sure of that. Okay, now I'm going to divide that by 30.8. Now all I need to do is add to it I'm going to go ahead and do the math on this one. So 1 divided by 353.25 equals 0.0028309. I'll stop there. And of course it's all this, 1 divided by all of that, right? So I'm going to run that over and I'm going to go, hey, it's 1 divided by whatever all this comes out. So I got the 93.4 divided by 101.3. Times 8.3145 equals divided by 30.8 equals plus 0.0028309 equals negative 0.04966, we'll call it, right? Well, it doesn't like that answer, does it? Double check it. 8.3145 times the natural log of 83.4 divided by 101.3 kilopascals. Oh, my friend, we have to convert this into joules.
Oh, that's why it's going wrong.
I know it works. I did it earlier. All right. 8.3145 times the natural log of 83.4 divided by 101.3. Okay. Divided by 30800 equals plus 1 divided by 353.25 equals, and now I find the inverse of that, and I get basically 360. Is that what they get? It's close.
No. Hey, Mr. Douglas.
Hello.
Huh?
Not a care that there's a class going on. All right.
I got 359.81.
That's what I just came out with too. That is not the right answer. The right answer is 346.9. I'm not sure what we're doing wrong. We have plugged everything in correctly. And like I said, I did this. I did it on my computer. You know, type it all in, and it's like, yeah, that's right. Anyway, the math is right. The equation's right.
Yeah, the equation.
Okay, let's take a run at the next one. See if we do any better.
Okay.
For acetone, the normal boiling point is 56.5 degrees centigrade. So that's what, 101.3 kilopascals? Is that correct? 101.3. Okay, good. And enthalpy of vaporization is 31.3 kilojoules per mole. Okay. And we want to know the vapor pressure at 25.0 degrees centigrade. Okay, so this time what are we doing? We're trying to find, instead of finding T2, we're trying to find vapor pressure. Let's erase this. Do a little more algebra. All right, what are we trying to solve for?
P2.
P2. Okay. All right, so we're going to begin on this side.
You can break down the natural log of P. If you build natural log of P2 minus natural log of P1. And that's easy. Because now you can just put P1 to the other side and that's it.
That gonna work?
Usually it works.
This is beyond me.
I mean, I'm not wrong.
Hmm?
If I'm not wrong, that's how it is.
Well, I hope you're not wrong. Should we do a little practice? We can confirm this, right? Natural log of 1/3, based on what you're saying, would equal the natural log of 1 minus the natural log of 3. Is that correct?
Mm-hmm.
Okay, so let's just do it. This would be negative 1.099. Okay. This is 0. 1.099. So 0 minus that works out for this. I'm assuming it's working out there. There we go. That's how I think. I don't really know what I'm doing. Let me test this and see if I
Yeah,
this
it
is
was
gonna
better to test it out.
All right. Well, that makes this super easy, right? Because I'm looking for P2. So all I have to do is go natural log of P2 equals.
All of that plus
I
natural.
just did way too much. Delta H of vaporization over R times 1 over T1 minus 1 over T2 plus natural log of P1. And then, what's the inverse function for the natural log? What do we call that?
I don't remember, but I think it's exponential.
It's e to the x. I remember getting made fun of when I would talk about the inverse log. My students would be like, you don't know what you're talking about, just hush. Well, what do you call it? And I can't remember what they call it. Just do it, do it. Okay. All right, so let's see what we got. Our delta H of vaporization is 31.3. No, it's in kilojoules, so we probably want to multiply that out, right? So 3, so 1, 2, 3. That seem about right?
Yeah.
Okay. Divided by 3145?
Yeah.
Okay. Times 1 over my T1 is 56.5 plus 273.15 is 329.65. Did you get that?
Mm-hmm.
Okay, good.
Yeah.
3.15 plus 25 is 298. Now I need to add to that the natural log of 101.3 kilopascals, right? All this equals the natural log of P2. Okay. So I can start plugging and chugging here, right?
Mm.
So 31300 divided by 8.3145 times, parentheses, 1 divided by 329. I put a plus, and that's supposed to be minus. Minus 1 divided by 298.15, close parentheses, plus the natural log of 1.3 equals get that?
Mhm.
Okay. So now, oh, 3.14115, 76594. 23? That's not the right answer.
I got 30.312997.
Good, you got the right answer. I pulled something wrong.
I just did E over that,
Yeah.
and then it got the right one.
Okay.
241576594.
So, I had a calculation error, but the correct answer, according to the book, is 30.1 kilopascals. Okay, we'll take it. All right. Well, do we have time for the next thing? That's the question. Where are we? Let's do that one. We'll stop there for today and pick up next.
Okay.
Yeah. Okay. All right, my friend. Have a blessed day.
Thank you.